Welcome back. In this video, we will learn about the VSEPR theory, and then we will determine the polarity of molecules. Please have your periodic table, your electronegativity chart, and your VSEPR chart handy as you take your notes. The VSEPR theory is the valence shell electron pair repulsion theory. It predicts and explains the shape and geometry of molecules. Bonding pairs and non-bonding or lone pairs of electrons around a central atom of a molecule repel one another. The negatively charged pairs of electrons will repel with electrostatic forces, and these forces between the pairs of electrons cause them to move as far apart as possible from each other. Lone pairs will repel more than bonded pairs of electrons. Some vocab to be familiar with. Bonding groups. A single, double, or triple bond around a central atom counts as one bonding group of electrons. Lone pairs of electrons are non-bonding pairs of electrons around a central atom, and they are not shared with another atom. Electron domains. This is the total number of bonding groups and lone pairs of electrons around the central atom. In our water molecule, we have 1, 2, 3, 4 electron domains. This carbon atom has 1, 2 electron domains. Bonded pairs of electrons and lone pairs of electrons affect bond angles differently because lone pairs repel more. Because they are closer to the atom, they force nearby bonded groups further away, causing smaller bond angles than expected. So if we look at this linear molecule over here, we have a bond angle of 180 degrees. When we add a lone pair, it repels more, so it forces the two bonded pairs of electrons closer together, reducing this bond angle and making it smaller. Adding two lone pairs will repel even more, and that bond angle will become even smaller. Depending on the structure of a molecule and the number of bonding groups and lone pairs of electrons around this central atom, we can predict molecular geometry or shape of the molecule. We can also predict the electron pair geometry, and that one considers all the bonds and electron pairs, in other words, all the electron domains around the central atom, not just the bonded atoms. This is your VSEPR chart that you were given. You will not be given this chart on tests and quizzes. You have to memorize the electron pair geometry, the molecular geometry, and the corresponding bond angles on this chart, and be able to predict that for molecules. On the chart in this column, A is the central atom. X represents an atom bonded to the central atom A, and E represents a lone pair of electrons on the central atom. The VSEPR theory focuses on the central atom to predict molecular and electron pair geometry. Let's practice reading this chart by doing a few examples. First, we have to draw the Lewis structure for the molecule. And establish how many bonding groups are around the central atom. So for beryllium difluoride, we have 1, 2 bonding groups. Next, establish how many lone pairs are around the central atom, and we have none for this molecule. Using these two criteria, I end up with a bond angle of 180 degrees, and that matches a linear molecular geometry or shape. For the electron pair geometry, I add up the number of bonding groups, 2, plus the number of lone pairs, 0. That gives me a total of 2 electron domains, and that matches a linear electron pair geometry as well. For sulfur dioxide, I draw the Lewis structure. Looks like this, with a lone pair. I count the number of bonding groups. I have 1, 2 bonding groups. Remember that double bonds count as one bonding group. I have 1 lone pair above the central sulfur, and the lone pair reduces my bond angle to less than 120 degrees, and that matches a bent molecular geometry. For the electron pair geometry, I count the total number of electron domains. So I have 2 plus 1 is 3, and that matches trigonal planar for the electron pair geometry. For boron trichloride, I draw the Lewis structure. I count the number of bonding groups. I have 1, 2, 3 single bonds, 3 bonding groups, no lone pairs on the central atom. All my bond angles will be 120 degrees, and that matches a trigonal planar molecular geometry. For the electron pair geometry, I have 3 bonding groups, 0 lone pairs, total of 3 electron domains, which is also a trigonal planar electron pair geometry. This is also a part of the front page, so you do have to memorize the rest of these shapes, and you will need to practice some more. This is the back page, and you do not have to memorize that side. Same thing, this is part of the back page. Now I want you to pause the video and to practice finding out the electron pair geometry, molecular geometry, and bond angle for all these molecules. You can use your reference chart in the beginning, but as you go along and get more familiar with the different shapes, you have to try to memorize your reference chart until you are able to do the molecules without looking at the chart. These are the correct answers. Let's look at molecular polarity. If you remember, a polar covalent bond is characterized by an unequal sharing of the bonding electrons. A dipole is formed in which there is a partial negative charge on the atom that is more electronegative and a partial positive charge on the less electronegative atom. So looking at the chlorine molecule, same electronegativity, nonpolar bond. HCl, chlorine is more electronegative, so we have a polar bond. A polar molecule is one that has a positive and negative pole, and the extent of the polarity is called a dipole moment. Bear in mind that the existence of a polar bond in a molecule does not necessarily make the molecule polar. We have to consider geometry and symmetry also. So if we look at carbon dioxide, it has 2 polar bonds, and yet it is a nonpolar molecule. Water also has 2 polar bonds, but water is a very polar molecule. So we'll find out in the next slides how we determine polarity of the whole molecule. For diatomic molecules, determining molecular polarity is easy because there are only 2 atoms, so the polarity of the molecule has to be the polarity of the bond. And we look at that by looking at the difference in electronegativity between the 2 atoms. In a hydrogen molecule, the difference is 0. So we have a nonpolar bond and therefore a nonpolar molecule. In HCl, the difference is 0.96. So we have a polar bond and therefore a polar molecule. When we have molecules with 3 or more atoms, we have to look at the symmetry, the molecular geometry, as well as the polarity of the bonds. So generally, molecules that are completely symmetrical are nonpolar, even when they contain polar bonds, because the dipoles end up canceling each other out. So let's look at carbon dioxide, why it's nonpolar. We do have 2 polar bonds, with oxygen being more electronegative. So we draw the dipoles like this. However, because carbon dioxide is completely symmetrical, the 2 dipoles end up canceling each other out, and we end up with a nonpolar overall molecule. In boron trihydride, we have 3 nonpolar bonds, and we also have perfect symmetry, so we end up with a nonpolar overall molecule. Similarly, in methane, we have 4 nonpolar bonds. We have a completely symmetrical molecule, so we end up with a nonpolar overall molecule. In carbon tetrachloride, we do have polar bonds. We have 4 polar bonds where chlorine is the more electronegative atom. However, again, this molecule is completely symmetrical with the 4 chlorine atoms around the central carbon atom and all the bond angles being the same. All the dipoles cancel each other out, and we end up with an overall nonpolar molecule. Now let's see how asymmetry can affect the molecular polarity. Asymmetry can stem from different atoms having differences in electronegativity across bonds bound to the central atom. So we've looked at carbon tetrachloride being completely symmetrical and therefore nonpolar. But if we replace one of the chlorine atoms with a hydrogen atom, now we have 3 extremely polar bonds between carbon and chlorine. And we have a nonpolar bond between hydrogen and carbon. So what we end up having is a dipole moment that makes this chlorine side of the molecule more negative than the hydrogen side of the molecule. So we end up with a polar molecule because of this asymmetry. Asymmetry can also come from the central atoms containing asymmetrical electron pairs. So let's compare boron trifluoride and ammonia. In boron trifluoride, we have 3 polar bonds. But again, due to the symmetrical nature of this molecule, they cancel each other out, and we end up with a nonpolar molecule. If we look at ammonia, we have 3 hydrogens bonded to a nitrogen, but we have this lone pair of electrons over here. So this time our molecule is not symmetrical anymore. We have 3 polar bonds between hydrogen and nitrogen, with nitrogen being more electronegative. And we have this lone pair of electron on the nitrogen atom. So we end up having a dipole moment where the nitrogen side of the molecule will be more negative and the hydrogen side of the molecule will be more positive. Comparing carbon dioxide and water, we have discussed carbon dioxide where the dipoles cancel each other due to symmetry, and we end up with a nonpolar molecule. In water, we have 2 lone pairs of electrons on the oxygen atom. So we have 2 polar bonds with oxygen being more electronegative. So we have an overall dipole moment towards the oxygen being more negative, and we end up having the oxygen side of the molecule being more negative than the hydrogen side of the molecule. And water is very polar. This concludes video 5. Come to class prepared with your notes as usual.